Hello, everyone. Welcome to the first in a series of online lectures for ESC190. So today we're basically going to cover more of the complexity and analysis of some of the search and sorting algorithms that we went over in the last week Friday. But just before we start that, I do want to say that due to the extenuating circumstances that we are going through right now, I wanted to say that the other topics that you would see in your syllabus, like game tree search and dynamic programming, they will only be bonus material for ESC190. So they may show up, in Lab 5 or the exam, but they will only be bonus material for extra marks. Okay? All right. So let's try to review what we went over in the last lecture. So let's start off with search. So if you remember, one of the efficient search algorithms that we went over was binary search. So okay, so binary search, remember, if you're given a sorted array, we want to find the index of a certain key. So for example, if we had, these numbers, 1, 3, 8, 10, 11, 13, and 14, and let's suppose we want to find the index of 11. So we want to find this guy over here. So remember what the general thing that we do is first we're going to set some left index. So let's say this is L, and this would be equal to 0. So each of these guys has their own index. And 6. This would be our left, or our lower index. This would be our upper. And then we would compute, the median of these two indices by setting m equal to, L plus u minus L over 2. Okay? And remember, the reason why I'm doing it in this way instead of, say, just something simply as like u minus L or u plus L over 2 is because, when you're programming, you want to avoid any possibilities that we might run into overflow. Okay? So we're just going to go over, this way of doing it. L plus u minus L over 2 is the mid. And when we find that, we should get 3. So m should be equal to 3 over here. And now all we do is we look at the number here, 10, and we compare that to 11. We see that 10 is smaller than 11. So we know that 11 has to be somewhere to the right of this. So what we do is we effectively cross out, this part of the array. We set L now equal to m plus 1, and then we just recompute m. So this now becomes, 4 plus 6, 10 divided by 2 is 5. This now becomes our new m. And then you just repeat the process. So we check out what is the array at index m. We see that it's 13. And 13 is now larger than 11. So now we know that we have to look at the array to the left. So we cross off this part of the array. And now, we would set our u equal to m minus 1. So this becomes u. And then we would recompute m, which is just this plus this over 2. So of course, it's just going to be right here. We check out what is the array at index m again. So this is the third iteration that we're going through in our loop. And we see that array at m is indeed equal to 11, which is what we wanted to find. So now we're done. And we would return 4, because this is the index that 11 is located at. OK? So this is all review. But if you remember, I said in the last lecture that the time complexity for binary search would be in log n time. So, and you can kind of intuitively see that because you're kind of chopping off half of the array at a time. So specifically, you would expect log base 2 of n comparisons that we have to do on the median elements. Okay? But let's try to look at that a little bit more rigorously. So analysis of binary search let's let a function called t of n be the time complexity of binary search on an array with n elements. Okay? So t of n is how many computations, or let's say comparisons, that we have to do here. It could be comparisons. It could be how many times we need to compute m equals l plus u minus l over 2. How many times do you have to do that? In total would be t of n for this entire algorithm. So let's try to write it out. We have t of n. Now what we're going to write is something called a recurrence relation. So this is going to be called, or let's say this. So this is going to be a recurrence relation, which is basically a function that relates a running time to running times on smaller problems. Because basically, whenever we did the binary search, when we iterated through, we were kind of solving the same problem over and over again. So what we could say is that t of n, whenever we have an n value, so if we have, let's say, one array element, that's kind of like a base case, right? If we have one array element, we're just going to end up returning, either it's not there or that is equal to like 11 or something. So we could say that t of n is effectively equal to just 1 if n is equal to 1. And if n is larger, so like in this case, we had 1, 2, 3, 4, 5, 6, 7 elements. Well, t of n is just going to run in t of n over 2 plus, let's say, c, if n is larger than 1. Okay? And basically, what I'm saying is that we divide the problem in two. This is what I mean when I talk about divide and conquer. So, I effectively crossed off, in the first iteration, half of the list, and then I solved the same problem, on the other half. So t of n is going to be t of n over 2. So solving the problem on half of the array, plus whatever constant number of operations I need to do, when I was, computing m equals L plus u minus L over 2, or comparing the array at, index 5, 13 to 11. So that's like 2 operations that I had to do, but I know that it runs in constant time because it's just, 2 operations. Okay. So yeah, let me just, write that down. So this would be, this c is basically the time needed to compute a new m, and checking the array at index m. Okay? So that's the recurrence relation. And one way that you can actually solve recurrence relations is to draw something called a recursion tree. Okay? So let me just draw it up here. So recursion tree So we're going to consider t of n again, okay? And what we're going to do is we're going to try to write out all of, the terms that are entailed in that equation there. So we have t of n, we know that, from looking at a top-down perspective, okay, that we have, t of n consists of c operations. But in addition to those c operations, it's also going to have t of n over 2 operations, right? So adding up c and t of n over 2. But t of n over 2, that also has a relation. And that's also going to consist of c and t of n over 4, right? Because imagine you take that n over 2, and then we divide that n over 2 by 2. So it's going to be t of n over 4. So this is also going to have t of n over 2, squared. And then we just keep on going. So dot, dot, dot. And, eventually, we're going to keep dividing n by 2 over and over and over again until we get t of 1, which is our base case over there. So eventually, we're going to get t of 1. So let's just call, each of these levels of our tree here equal to d. So let's say this is d equals 1, d equals 2, and then so on. This d. Okay, so d equals something. And so the trick is, what we want to do is we want to kind of count how many nodes there are in this tree. Because that's going to tell us really how many times we have to do some sort of computation. But leaving it in terms of t of something is kind of, it's kind of abstract here. So let's try to write that in more concrete terms. So let's try to convert that. So we have our c, okay. Now t of n over 2, if we look at the recurrence relation, that's just going to consist of, your t of n over 4 and also a c. So we can also write that this is just going to be c and then our t of n over 4. But t of n over 4 is just going to consist of, c and t of n over 8, right? So we can write c, and really we can just keep on going over and over and over again until we reach our t of 1, which is just going to be, 1 over there. So we want to sum all of these nodes, okay? I want to sum all of these nodes. And the way to do that is we're going to need to know how to predict what is this final D level. What is the depth of this tree? Okay, so the goal is sum all nodes in the tree and how many levels are actually in the tree. That's the question. Okay, so what we can do, to solve this is, each of these little terms here is going to be n over 2 to a power. So in this case, it's n over 2 to the 1. This is n over 2 to the 2. And you can kind of see a pattern here, right? This is basically just n over 2 to the d. So what we want to find is when is n over 2 to the d equal to just, this term here, so t of 1. Okay, so we can solve for d. And we know that d will just be equal to log base 2 of n. Okay, so, and we know that t of n in total is just going to be the sum of all the c's, from 0 to the final level of d. So we'll get that t of n is just going to be equal to the sum from I equals 0. So from up here to, d of c. And right, I realize now that I actually put a 1 up there, but actually, you probably may have caught this by now, but if we want it to be as general as possible, it should also be a c. So I'll change that 1 to a c very soon. You would get a sum of I equals 0 to d of c, which is just going to be the sum of I equals 0 to log base 2 of n of c, which is just going to be, since c is just a constant term, you can get that out of the sum, and you will get c times all of these terms. So 0, 1, 2 to log base 2 of n. So you'll get c times log base 2 of n plus 1, right? And then this is just equal to, well, c log base 2 of n plus c. So we've basically just proven that t of n is in theta of log n. Okay? So that is more of a rigorous proof, to actually show what is the complexity of an algorithm like binary search. Okay, so let's just change that to C, change that to C. Okay, so that was binary search. Let's move on to the other search problem that I presented, was finding the kth smallest element. Okay, so finding the kth smallest element. If you recall, that had to do with, kind of like quicksort, except we only look at, one side of the array. Okay. So just to, briefly review, let's suppose we had, okay, so this is kth smallest search. So basically, if we have, n elements that are not sorted, we want to find what is the kth smallest element in that whole array. So let's suppose we had, like this, 8, 5, 10, 17, 4, 3, 7, and 6. And let's set k equal to 3. If you remember the partition step, we will choose, a pivot, out of one of these elements, and then we'll just partition the array around that pivot. We'll look at the index of the new index of that pivot, and then we'll compare that to k. And then based on that, we'll know whether to look at, the left half or the right half of the array. So let's do it again. Let's choose, 6, as our pivot. Okay, so this is our pivot. And let's partition the array around that. Now, I'm not going to go into it in too much detail because I did go over it step by step in the last lecture. But the result of that, will be something like this. I have 5, 4, 3. Then we have 6, our pivot. Then we have the rest. So 8, 10, 7, and 17. And, just to keep track, this is index 0, 1, 2, 3, 4, 5, 6, and 7. What we care about now is where is the new index of our pivot 6. So we see that our new, let's call it new index, is now equal to 3. And now we got to compare 3 to k minus 1. So 3 is larger than k minus 1, which is equal to 2. And why are we doing minus 1? Well, look over here, right? So 6, it's here. Now, what we know so far is that 6 is the 4th smallest element of the array, right? Because everything to the left is smaller, everything to the right is larger. So we are guaranteed by looking at this, this is 3. Since we start at 0, we would have to compare it to k minus 1 instead. So k is 3, minus 1 is 2, and it's larger than that. So we almost found the 3rd smallest element, but we're off by 1, so it's actually the 4th smallest. But that's already great information to know. Since this is the 4th smallest element, and everything to the left is smaller, well, the 3rd smallest must be in one of those elements there, right? If it was the other way around, let's suppose, we were looking for, or let's suppose, k happened to be, 5 instead. We wanted to find, the 5th smallest element. We would compare. This would have a comparison of 3 smaller than 5 minus 1 is 4, and we would know to look to the right of the array instead. So given this, it's larger, we know that we can just cross off this part of the array, and we can only focus on the left part to find the 3rd smallest element. Okay, so we can continue. Choose this as the pivot, and this is the pivot, and we want to partition the array again. We could have 3 over here, we could have 4 and 5. So we're moving everything larger, 5 and 4, to the right, and there's nothing that's smaller, so this is the first. 3 will end up being the first element. And now our new index becomes 0. Okay. Now 0 is smaller then k minus 1 equals 2. So since it's smaller instead, now we know that we need to look, well, to the right of this. However, we did find the first smallest element because, new index is 0. 0 plus 1 is 1. We know that at least we found the first smallest element. So we found the fourth smallest element, we found the first smallest element, and we're slowly converging towards getting the third smallest element here. Okay, so we cross that off. This guy is already, crossed off, and now we're only going to focus on these two elements here. So we can do the same process. We can choose 5, the last element, why not, as the pivot. And, when we move this, we partition this around, nothing much is going to happen because it already happens to be sorted. We're just going to end up with 4 and 5 again. And now, our new index is going to be this, which is 2. Okay, new index is 2, and that is equal to k minus 1 equals 2. Now, since it's equal, now we know that we have found the kth smallest element, so the third smallest element, and we can, confidently return the array at new index, which is 5, is our third smallest element. Okay? So we return our, at 2 now, is equal to 5. So remember, we couldn't do that at the beginning because the array was completely in a different order. We had to do all of these partitions, and we had to swap around elements around, and then we could actually, find this, just compute R of 2. Okay? All right. So that was, a review of how to do the kth smallest element step by step on the board. Now let's try to analyze this as well. Okay. So if we analyze what we did here, we're going to look at the average case. So if you remember, the worst case of this running time complexity is if we just happen to always select the pivot as the largest element. And now if we did that, we would keep on having to repeat the same problem on n minus 1 elements, then n minus 2 elements, and so on. And that'll lead to a worst case of n squared. And the reason that is because you would get t of n. So let's say this is, well, let's just write out what the worst case really looks like here. So, let's just write it out. 3, 4, 5, 6, 7, 8, 10, 17. So basically the same numbers, but it happened to be sorted now. So imagine we were to select 17 as the pivot. 17 as the pivot. We do some partitioning, which is basically nothing, because everything to the left of 17 is already smaller than 17. So we would cross this off, and then we would repeat the same problem on this. On this guy over here, we'd choose this as the pivot. And then, well, OK, it's already sorted. Don't need to do anything. Cross that off. And then so on, right? We would keep on going. And we would keep on, remember in the partition operation that required n operations to go through the entire array. So first, we would go over from here to here, then here to here, then here to here, then here to here, and so on. So what we would get is that t of n is going to be equal to the sum from I equals 1 to n of, basically I. And if you're to add all of that up, you should get half of n times n plus 1, which is O of n squared. Okay? So that's why it's in O of n squared. And that is the worst case that we can possibly get. So basically, we're doing n plus n minus 1 plus n minus 2 all the way to plus 1. Yeah, so that's the worst case. Now, more interesting case, we can say is the average case. And the average case, if we were to choose our pivot, really like randomly, per se, then, half of the time, we might eliminate, 8/10 of the array. The other half of the time, we might, eliminate maybe 2/10 of the array. It might be 7/10 of the array, 6/10, so on. But on average, if you're to consider all the different cases of how we are going to partition the array based on the randomized pivot, we would actually find that on average you're going to eliminate half of the array at a time. So the recurrence relation of that would look something like T of n would be C if n is equal to 1, and T of n over 2, plus some constant, times Cn if n is larger than 1. Okay? So this C times n, that just corresponds to, in the partition operation, you have to go through each element, at a time, and actually swap elements around. So it might be some constant multiple of C, times n. Okay? And if you were to draw this recursion tree, you would get something like, T of n, which is going to be C times n. Then we would get T of n over 2. You would get T of n over 2 squared, and so on, until you get T of 1. So, and again, this is just C because you have C times n equals 1. So C times 1 is just C. So these are basically kind of like the same operation here, or set of operations. Okay. So if we have this, so this is our recursion tree. We have this, and just like how we did for binary search, we can try to simplify this more. We would get C times n, but T of n over 2 is just going to be, well, C times n over 2. We have C n over 2. Here we have C n over 4, and so on. Then you have just C. And now what we want to do, just like how we did in binary search, is just add up all of these terms. Okay? So it's not going to be as simple as binary search, since it's a little bit more of an involved expression. But luckily, since you guys are all taking Calculus 2, you all learned about infinite series. So now we're actually going to apply that knowledge to algorithms. Okay. So T of n Well, if you remember from what we did, which I just erased in binary search, the number of levels of that tree is just going to be log base 2 of n, basically. Or to be precise, log base 2 of n plus 1. Okay, so T of n is going to be the sum. Okay, it's going to be the sum of, from I equals 0 to log base 2 of n of c, so c times n over 2 to the I, right? Because the first one, 2 to the 0 is 1. So you have c times n, then c times n over 2 to the 1, and so on, until you get c at the very end. So this is what we want to compute. And we can go ahead. We can say that, OK, this is, you can factor out the cn and only have the 1 over 2 to the I. So you can have cn sum from I equals 0 to log base 2 of n of, well, 1 over 2 to the I is just half to the ith power. Okay, so that's an I. And hopefully some of you are starting to see how this looks very familiar. There's a certain series that this looks a lot like. And that is, well, that is a geometric series. And maybe, if you want to be really precise, you wouldn't call it, a series because I haven't, let this go to infinity yet. But we will soon. So you have a geometric series. And, if you remember, the formula for, the geometric series up to a certain number of terms, you're just going to get Cn. You'll get, this is kind of like your R term, half. You get 1 minus half to the log n plus 1. Over 1 minus half. Okay? So 1 minus r. Now this is a little bit messy. Usually when we want to find a complexity, we like to have, nicer expressions that are easier to present. So what we can do is actually find an upper bound for this. And what better upper bound than to just let this term go to infinity? Because we know that a geometric series will, converge if our r term, absolute value is, less than 1. So we can say that T of n is going to be, less than, Cn sum from I equals 0 to infinity. Nothing wrong with saying that, of half to the I. And this is just going to be Cn 1 over 1 minus half. So you can remember this from your calculus course. And this is just going to get you, so 1 minus half is half, 1 over half is 2. You will get 2 Cn. Now 2c is just a constant. And now we're just left with our n term. So hence, this is an O of n. And I'm writing big O because I found an upper bound. Okay? So that's why it's important to, make sure you're using the right, asymptotic notation here. So hence, you can see that, on average, if you're to use like randomized partitions, randomized pivots, then this will run in O of n time. And that is why this is one of the more efficient approaches to finding the kth smallest element. OK. So that was an analysis of the kth smallest element. And another algorithm that we went over was merge sort. So the merge sort, let's look over that in a little bit more detail. Merge sort, we have something, like T of n. And remember, merge sort is a lot like binary search, except we look at both halves of the array. And because of that, the recurrence relation is really just going to be almost the exact same, except a little bit more interesting. So we're still going to have our C term if n is equal to 1. But now, instead of just having T of n over 2, we're going to have 2 times T of n over 2. 2 times T of n over 2 plus, a constant number of operations for actually merging, the two arrays together. Okay? Now, if we were to draw the recurrence or the recursion tree, for this, is going to look a little bit more interesting. So at the top, we might have Cn. But now, instead of just having, one child in the tree, we're going to have multiple. So we're going to have T of n over 2. This is going to be T of n over 2 as well, because we have 2 of them now. And then for each of these, this is just going to have, T of n over 4, T of n over 4, and so on, right? Yeah, and this is just going to keep on going. Like this, until we get a bunch of T of 1 terms at the very bottom. Okay? So now this is what the recursion tree is going to look like. So, we can, again, just like how we did in the other recursion tree, we can just replace each of these terms with, actual concrete terms in terms of like, C times n or something. In this case, this would just be C n over 2. This would also be C n over 2. This would be C n over 4. And you're starting to get the idea. So to analyze this, again, just like how we do before, we want to add up all of these terms together to get a final answer for what T of n is going to be. Now, just like before, each level, let's say that we have level I, let's say. So this is I equals 0. This would be I equals 1, I equals 2, and so on. What we can count is that each level is going to have 2 to the I nodes. So we have 2 to the 0, 2 to the 1, and and so on, 2 to the 2. Okay, so that's great, but we also know that each node has a cost of C times n over 2 to the I. So what we have is that each level has a cost of 2 to the I, so the number of nodes that there are at the level, times C times n over 2 to the I for the cost of each node. And if you multiply that, you'll get Cn. So Cn over 2 plus Cn over 2 is also Cn, and so on. So you can kind of see that, diagrammatically from the tree. So that's great. Every level is Cn. And just like with binary search, how many levels are there? Well, it's going to be log base 2 of n plus 1. Right? So that means, let's move on over here, that our total t of n is just going to be Cn times log base 2 of n plus 1, which is equal to Cn log n plus Cn. Okay? Now, we know that Cn log n grows a lot faster than Cn. So this term is really what's going to dominate here. And hence, merge sort runs in theta of n log n. Okay? So theta of n log n is the running time for merge sort. And as an exercise for you, I would say try to write the recurrence relation and also the recursive tree for quicksort, the other sorting algorithm that we went over in the last lecture. And try to write the recurrence relation and recursive tree for either the worst case, where it's already sorted, or the best case, where the pivot we choose always happens to be the median of your array. Okay? And yeah, I think that's pretty much it for the lecture. In the next one, we will cover graph applications, so more in-depth applications of depth-first search and breadth-first search, and we'll also get into implementation in the C programming language. Thank you.